Welcome back. In this video, we are going to talk about the conservation of momentum. So what we have in the figure in the left are two skaters, skater A and B, and these skaters are exerting forces on each other. So you have the skater A is pushing skater B to the right, and then your skater B is also pushing your skater A to the left. Now in this case here, we have other forces. You have the force due to gravity or the weight of the skaters, which is downward, and the normal force, which is acted on by the surface to the skaters. So in here, we have external forces. This is different with the astronaut's situation, which we have discussed in the previous video. Here, external forces, the normal force and gravity act on the skaters, shown in the left. But as you can see, the normal force and then the force due to gravity cancels out. So the vector sum of these two forces are zero. Therefore, we can still say that the total momentum of these skaters is conserved. So what's the conservation of momentum? So the conservation of momentum states that if the vector sum of the external forces on a system is zero, the total momentum of the system is conserved. So again, if the vector sum of the external forces in the system is zero, then the total momentum of the system is conserved. Even though we have external forces like the normal force and gravity in our situation, but the vector sum of these forces is zero. So still, we can still say that the momentum of the system is still conserved. If the net force acting on an isolated system is equal to zero, that is the vector sum of all your forces, external forces is zero, the total momentum of the system is constant. And we can say that the momentum of the system before the collision is equal to the total momentum of the system after your collision. That is, you have your P system, your momentum of the system before your collision is equal to the momentum of your system prime, which is after your collision. So your prime symbol here on your equation will tell us that it is an event which happened after your collision. And this law of your conservation of momentum is true for all types of your collision. In the next slides, we are going to talk about your collisions. Remember first that the momentum is a vector quantity, since your velocity is a vector quantity. So a system of two particles with momenta in different directions, like this one here. One of the particles moving upward, your PA, and your second particle moves to the right, your PB. You cannot find the magnitude of the total momentum by just adding the magnitudes of the individual momenta. So it's wrong to say that the momentum of your system is equal to your PA plus your PB, which is equal to 42 kilograms per meter per second. Because again, your momentum is a vector quantity. So you need to add the components of this vector in order to find for the total momentum of your system. So instead, we use your vector addition. So in this case here, we're still going to use the lessons that you have learned in your vector addition. When applying conservation of momentum, remember that momentum is vector quantity. Use vector addition to add momenta, as shown in the figure to the right. Now, what are collisions? So when we say collision, this is a strong interaction between objects that last in a relatively short time. Like say, for example, when you're going to play billiards. So you're colliding the balls in order to drop it into the specific targets, right? So the collision or the interaction between your billiard balls, like in the figure, is what you call a collision. So since collision is a vector quantity, we have your conservation of momentum in one-dimensional collision. So this is just here your P system, your momentum of your system before collision, which is equal to your P system prime after your collision. So everything that is on the left of the equation are your before collision quantities, and everything to the right are your after collision quantities. And here, if your system is isolated and there are no, or if the sum of the external forces are zero, then your momentum should be conserved, which can be expressed in its XYZ components. So you can have your momentum along the X, along the Y, and then along the Z. So are just the sum, or the these are your law of conservation of momentum formulas, which you can use later in solving problems. Now, collisions happen in anywhere around the universe. So you know collisions of cars. So when you're colliding cars or when you hit another car, that's a collision. And collision even happens in the atomic scale, in the subatomic scale, that like what is done at CERN. So if you were quite curious with the pictures we have used in the beginning of the slides, that is actually an actual experiment at CMS at CERN, which is in Geneva, Switzerland. So the concepts used here is that you have they are colliding particles. You're smashing particles together to form other subatomic particles, and you're going to study these subatomic particles to find strange and new ones. So the concept here, even at the subatomic scale, is your conservation of momentum. And collisions even happen at the universe. So we can observe actually galaxies colliding with each other and merging to form bigger galaxies. So collision is everywhere. So we actually have two types of collision. We have your elastic collision. When we say elastic collision, the total kinetic energy of the system is the same after the collision as before. So again, the elastic collision is the total kinetic energy of the system is the same after the collision as before. So that means that the kinetic energy of your system is the same to your kinetic energy prime. So this is before collision, and this is your after collision. On the other hand, the inelastic collision is a collision wherein the total kinetic energy after the collision is less than the before collision. So here, in inelastic collision, the kinetic energy is not conserved. So kinetic energy is not conserved. We have a special case of an inelastic collision, wherein a collision in which the bodies stick together after colliding, and an inelastic collision with this type of case is what you call a perfectly inelastic collision. So again, when we say perfectly inelastic collision, this is when after colliding, the two bodies or the bodies stick together. So in any collision in which the external forces can be neglected, the total momentum is conserved. So both for your elastic collision and inelastic collision, the total momentum of your system is conserved. It's just that in your elastic collision, the kinetic energy is conserved, whereas in the inelastic collision, the kinetic energy is not conserved. By the way, what you see in the image is your rocket. So your rocket propulsion is actually a reverse of your perfectly inelastic collision. So in your perfectly inelastic collision, after colliding, the two bodies stick together, so their masses combine. But in your rocket propulsion, so your rocket propulsion, so what you actually have here is at the beginning, uh, how do you draw a rocket? So at the beginning, you have your rocket plus your gas or your fuel, okay? And when the rocket is launched, you will observe that the rocket actually expels your fuel. So it's a reverse of your perfectly inelastic, because in the perfectly inelastic you have two bodies that when they are going to collide with each other, they stick together. But here, you have first the rocket plus the gas, and then after that one, when you're going to launch the rocket, the the rocket will expel this gas, so the gas. So it's a reverse of your perfectly inelastic collision. So this one, you can still call this one as a collision, which is just a collision in reverse. So that's how you're going to propel your rocket. Let's discuss your collisions in more detail. So let's discuss first your elastic collision. Uh, we have these collisions which we call your head-on collisions. Your head-on collisions happen when the center of masses of your system or of your bodies align. Like say for example, if you have this one here, the ball one with the center of mass here, and then another ball here with the center of mass here. Now, if in their collision, the two center masses of your two objects align, you call this one as a head-on collision. So we have here a head-on collision for an elastic collision. So before collision, we have one object or mass one, which is moving to the right, and then mass two, which is at rest. So during collision, they stick together, but after the collision, what you observe is that your what you will observe is that the velocity of your ball one will be zero. It comes to rest, but it will transfer it will totally transfer its energy to mass two. So again, we've said that you're in your elastic collision, your k initial is equal to your k final. Okay? So your kinetic energies are conserved. So what just happens here is that the energy of mass 1 is transferred to mass 2 totally. Another example of a head-on collision is when you have your mass 2 and then your mass 1 moving towards each other. Let's say that they are moving at the same speeds and at head-on collision. So that is before collision. And then once they collide, they stick together momentarily or they interact momentarily. And then after that one, they split. They move at, at some velocities b prime. Another example is for non-head-on collisions. So when you have a non-head-on collisions, the center of masses do not align during the collision. So let's say that your M2 is again at rest, and then your mass 1 is going to hit your M2. Okay. If you're familiar with your billiard balls, you will see that um, for a non-head-on collision like this one here, your mass 1 will still move to the right, but at some angle theta 1, and then your mass 2 will also move. It will move downward with some theta 2. So they will they will separate, and they will move at some angles with respect to the horizontal that we are talking about. So this is for a non-head-on collisions. This is the technique when you're going to use when you're going to play your billiards, and billiard players knows this one very well. Let's go to your inelastic collision. So we have a head-on collision, which is an inelastic collision. And by the way, this is an example of a perfectly inelastic head-on collision. So M2 is at rest, M1 is moving towards M2. They will momentarily interact during collision, and they will move together at the same velocity b. So again, this is an example of a perfectly inelastic collision. So what's important here is you have to take note that the kinetic energy of your system for inelastic collision is not anymore conserved. For a head-on collision, this is still a perfectly inelastic collision. You have the same, your mass 2 is at rest, your mass 1 is moving towards your M2, but this time this is a non-head-on collision. They will interact momentarily during collision, and after the collision, they're going to move together as one. Well, you can put this one here, like say for example, you can put the magnet on this side here of your balls so that they will stick together and then they move together as one with a velocity of b prime. So let us have here some simulations and let's see the collisions in real action. So let's look at your elastic collisions and inelastic collision, but just on head-on collisions. So we have here two masses, two cards. So during the inelastic collision, we have some springs here in the front end of your cards. Okay. The purpose of this spring is so that the two cards will bounce back after they momentarily interact with each other. So let's look at what happens with an elastic collision, and let's give the two cards the same velocity v. Okay. But initially, let's have your blue card to have zero velocity, meaning your mass 2 is at rest. And as you can see, the kinetic energy of card A was totally transferred to your card B, the blue card. So your red card stops and then your blue card moves. Now let's give your blue card the same velocity but in opposite direction. So as you can see, they bounce back, and as they bounce back, they still move with the same velocity. This time, let's have an inelastic collision, and let's have your blue card to be at rest momentarily. So they stick together. So there is actually a magnet on the front end of your cars to mimic your perfectly inelastic collision. Let's redo it. So they move as one with the same velocity, 2 meters per second. Let's do it this time when your cards both your cards have velocity. Both your cards have velocity. The same velocity at opposite direction. So what happens is they just stop and stick together. Now let's give your blue card a greater speed. So then they stick together, but they move together at -1. So this is a different case. So they stick together and move at the same velocity, 1.5 meters per second. So these are your elastic collision and inelastic collision. In your inelastic collision, we mimic your perfectly inelastic collision. There will be a lab activity for this one, which you're going to explore more about your collision cards.